now we will see the design of horn antenna and reflector antenna. Right. Now coming to the design of horn antenna. Now the horn antenna, initially if you can see on the left hand side we have a waveguide, right? And waveguide, and then we just flare the waveguide with an angle theta. Now this theta is the flaring angle. So in order to design a horn antenna, right, so we have to just calculate this theta value, right, so that based upon if the theta is maximum 90 degrees, then we have the maximum radiation from this particular horn antenna, right? So depending upon the flare angle theta, so theta we can just take it mathematically. Now how we do it is that, so consider this is the axis of the waveguide which has been extended, and this is your horn axis, and we can see this point at the waveguide at the last end, to the right end of the waveguide as O, and the other end of the horn is B, right? So OB, and the top of the horn antenna we have like C, so point C. So within right angle triangle OBC, if you can just calculate tan theta. So what is tan theta? Tan theta is nothing but opposite side by adjacent side. Opposite side is BC by OB. What is BC? BC from the figure, it is clear that it is as H by 2. So H by 2, and OB is L. So we have tan theta equal to H by 2L. Okay, then theta is tan inverse of H by 2L. Right, and similarly in terms of cos theta we know adjacent by hypotenuse. So if you can just see the cos theta function, the cos theta is that is from the adjacent is OB and hypotenuse is from O to C. So the equation, that is cos theta, is L by L plus del. About del is nothing but the path difference. So the del is the path difference, which is the difference from, that is we have OC. OC can be like L plus del. Okay, and then L, the equation of L in terms of del, we had a relationship that L is equal to H square by 8 times del. Now these are the equations which are used to design the horn antenna, right? And we can just have these as the formulas to calculate the half power beam width in terms of the electrical field and the magnetic field, that is as 56 lambda by H, right? And for magnetic field it is 56 lambda by W degrees, right? Then directivity we can just calculate with the formula 7.5 into A by lambda square, and A will be the height of the aperture, right? So C, that is the distance. Actually we have A, that is the aperture distance A, right? And then the power gain is given by 4.1 in times of A lambda square, where A is your aperture dimension, right, which has been taken as small h here, right? This is about the design of horn antennas. Now we go on with the reflector antenna. So what is a reflector antenna? A reflector antenna is a device that reflects electromagnetic waves in a desired direction. So till now we radiate the energy without any reflection. Now here we are using a reflector to reflect the signals, so it is named as reflector antenna. Why we use this is we can obtain high gain directivity, and it is used in very high frequency like microwave frequency, and it is also called as microwave antenna. So reflector antenna is also called as the microwave antennas. Now we can see the applications of this reflector antenna. So it has been used in satellite communication, TV signal broadcasting, wireless communication, radio astronomy, parabolic microphones, and lightning devices such as cars, LEDs, headlights, etc. Right. Now coming to its parabolic feeds. So we use a reflector, means here we use a parabolic reflector. So feeds which we use for this parabolic feeds, we can see the first one. This is the front feed we have, right? So in the slide we can just see this is the front feed. So we have a horn antenna, right? This is your horn, and this is your parabolic reflector. So this is your front feed, and Then waveguide horn feed. So this is like from the center it's coming, so it is an waveguide horn feed, right? And then next we can see here cutler, right? This is your cutler feed. We have a dipole disc. So from the center it emerges from the reflector. And then offset feed where it will be above the reflector. Now if this is the reflector, right, this is the reflector we have, and this is dotted line, that means it is not an reflector, it is above that. That means we are just making it up, so it becomes an offset feed, right? And Cassegrain feed, in the Cassegrain feed we use an hyperbola, right? This is your hyperbola. In terms of your feed, it is an hyperbola, right? And so after this Cassegrain feed, Georgian feed we have. Georgian feed, it is another parabola with respect to the feed. So two parabolas. One is a parabola with respect to the direction, another parabola with respect to the feed. So if it is an hyperbola, it is as Cassegrain feed, or it is a Georgian feed, right? So these points as the focal point of the antennas. Fine. So, and different types of reflectors whatever we have. So we have just seen the curved reflector. We have different types like plane type, corner type, right? So, and parabolic reflector. So three types of reflectors we have, but mostly used is the parabolic reflector, right? So we have plane type reflector, corner type, and the parabolic type. Fine. Then this is the ray representation through the parabolic reflector. Now it is as transmitting or receiving. Now consider this figure shows it is transmitting the signals from a particular focal point F. And when it is transmitting the signal, you can see it is going, and from F the signals are coming out, and it is going and hitting the parabolic reflector. The signals are reflected out and forming the parallel beam, right? That means it is converting the circular wavefront to a plane wavefront. So it is a plane wave, it is a reflecting wave, right? So from F it will be like circular wavefront, and this parabolic reflector making that to a plane wavefront. Okay? And this is the radiation pattern of the parabolic reflector, where it has very good directivity with the minor lobes, right? And these are the curved reflector antennas which we have seen previously. Now, and this is the Cassegrain feeder, right? In Cassegrain feeder we have one problem as the blockages, right? So in order to avoid blockages, actually what we do, we go with the offset feed, right? So we go with the offset feed so that to avoid the blockages and also the spillover, right? Then, what are the advantages of this parabolic reflector? The use of parabolic reflector reduces minor lobes, so we can use to reduce the minor lobes, right? It offers high gain and directivity, right? And the amount of power wastage is comparatively less than the other antennas. So this parabolic antennas are uh, have very less uh, power wastage, right? And it provides flexibility in positioning the feed element. So depending upon the requirement, we can have offset feed, so where blockages due to the signals can be avoided. So it has that flexibility, right? The use of parabolic reflector helps to provide easy beam adjustment. So we easily adjust the beam, right? And what is the disadvantage of that? So the size of the structure is quite large. So parabolic dishes are very large in size, so that's a disadvantage. Second one, the overall cost of the system is high. So the system cost is higher. Then the small element of parabola, it causes some amount of power obstruction. So if we can have a small amount of parabola cause the power disturbances or obstructions. Okay. Now if we can see the design of the parabolic reflector, the only parameter which we have to design, the focal length to aperture ratio. So we see what is focal length to aperture ratio now. So it is like F by D ratio. So the F by D ratio should be maintained from 0.25 to 0.5. Okay. Now we can see this parabolic reflector, we have point O, that's the center of the reflector. Then F is the focal point, and D is the distance between the aperture, distance of the aperture, right? So this F by D ratio should be like, so for a better parabolic design, the f by d ratio should be like 0.25 to 0.5, right? So this is the geometrical constructions which we just made, so that we can just calculate the value of f by d ratio. So the f by d ratio we get, right? So from this, by taking some mathematical trigonometric form, so f by d ratio we just get here. So f equal to d by 4 the cot of theta naught by 2, right? So theta naught is the angle made from the focal point to this particular parabola, right? So this is how we have to design the parabolic reflector with these equations, right? So based upon the theta value, the value of f by d ratio changes. So accordingly, we have to consider according to our requirements. Sorry, excuse me. And thank you for watching these videos. Thank you. Thanks a lot. This is the complete second unit which we have discussed till now. Thank you so much.